Welcome back. Welcome back at our Open Value meetup. Now with a talk from Jan Ouwens. He's developer and architect at Joink. And he will tell us just enough about computer science for a busy developer. Take it away and good luck.
Thanks. So cool to be in front of real people again. It's been a while. So let's start with why. Why am I giving this talk? Well, it turns out that when you are a developer and you have coworkers, not all of them have a computer science degree. I know, right? But actually that's a good thing. Because if we had left IT to the computer scientists, stuffy people, things would be a lot more boring. We wouldn't have Pokemon Go or Wordle or any of those cool things. We wouldn't be in a situation where my mom can pick up a computer and use it and maybe not even hate it. So that's pretty cool, and that's because there are lots of people working in the field who don't necessarily have a computer science background. That said, it is still relevant to our day-to-day jobs. And if you don't have the background, you can do a lot of things, but basically almost all of the things. But still, it helps to know a few of the things that you learn when you do a computer science degree, just to do your job just that little bit better. And that's what I'm going to talk about tonight. So if you only remember one thing from my talk, you can zone out afterwards if you like, and you will still have learned something. It is this, the Morgan's laws. And if you study computer science, this is the way you would write it down. If you are a Java programmer, this is the way you would write it down. It is basically a way to rewrite your Boolean expressions. So both of these are equivalent to each other. And I will give you an example. So here's an if statement with a Boolean expression that is pretty hard to read for most people. And using the Morgan's laws, we can simplify it. So the first step is to take out some variables, local variables. You can do that in Java. And now you have a slightly simpler expression, which we can apply the Morgan's laws to. And this is it. This is how you would rewrite it. So if we inline the variables again, you get this. And then you can remove the not symbols and turn around the less than signs, and you get this. And now suddenly the expression is a lot more easy to comprehend. And this is something that I still do wrong. This was 2 weeks ago. I spent way too much time debugging something that I could have fixed just by applying De Morgan's law. So how do we know that this law actually applies? Well, the simplest way is to write down a truth table. False is 0, 1 equals true. And you just write down all of the possibilities and work it out and fill it in the table. And it turns out that they are equivalent. And we have one for OR, and we have one for AND. And this is how they work. So if you only remember 2 things from this talk, the second thing is write a truth table. If you have complicated Boolean expressions, it helps with figuring out what it means. Okay, so my name is Jan. I work for Joink. You may also know me from Equals Verifier, which is a project that I work on. And you can find me on Twitter. And I studied computer science, so you don't have to. So computer science is more than just a science. There's a bunch of interesting people as well that I want to introduce, just, to share the anecdotes, to make it a little bit lighter. The first one I want to mention is this one. So for all of you non-native Dutch people, you pronounce it Dijkstra. And he used to work at Eindhoven University, where I studied computer science. So that was very much influenced by his teachings. One of the interesting things about Dijkstra is that he is a pretty quotable person. So this one is a very famous one. Testing shows the presence and not the absence of bugs. There's one that relates to artificial intelligence here that is kind of funny. And he also has something to say about the basic programming language, which was my first language. I think I turned out reasonably okay, but, just as a disclaimer. And he is very famous. He was very famous for writing papers by hand and then distributing a couple of photocopies to his close friends, who would then make photocopies and distribute it to their friends, etc., building up a whole tree. He could go viral before we had the internet. Okay. Computer science is a relatively young field, but still there is a lot of interesting history. I will just mention a couple of highlights. So there's this guy. He was a logician, a mathematician, and it's because of him that we have the word Boolean. It's derived from his name. He invented the concepts. Another thing in the history of computer science is this, the Jacquard Loom, which uses punch cards to define a pattern so that it could weave a tapestry or a cloth or whatever. And it was the first thing that uses punch cards. And of course, Charles Babbage is famous for trying to build a machine that uses punch cards to do calculations. And later on, we actually succeeded in doing so. The first computers used punch cards. Babbage was the inventor of two machines, a difference engine and an analytical engine. They were mechanical contraptions that could do computations. Unfortunately, he was never able to actually finish one in his lifetime, but in 1991, some people actually built the thing and it worked. It worked, so that was cool. And then there was Hedy Lovelace, who was writing programs for his machine that didn't exist, but her programs were the first of their kind. And she was actually the first programmer. And you may be surprised, a woman doing programming, and actually in the beginning, up till the 1950s, 60s, maybe 70s, programming was actually considered a woman's job. Which is, somehow things changed. I don't know why. At the time, it was like the men were the architects and the women were the programmers. The architects in their ivory tower, they did all the thinking, and then we had the typist who could write the programs. That was the way they were thinking. But of course, everybody who has worked with an ivory tower architect as a programmer knows that that's not how things work, right? Programming is really it's a real job. It requires real thinking, and it's a shame that this balance has shifted so much. And these women who did the programming are often unrecognized. We don't know their names anymore. For example, these two, we don't really know. They are standing in front of ENIAC, the Electronic Numerical Integrator and Computer, which is the first real computer that was ever built. And it was about 170 square meters in surface. So nowadays we make them a little bit smaller. That's a bit about the history of computer science. So let's go on to the actual science. One computer scientist, very famous, that I want to mention here is Tony Hoare. He invented the null reference, and he calls it his billion-dollar mistake, because fixing null pointer exceptions through the course of many decades has cost, on average, on estimation, billions of dollars. So that's why he calls it his $1 billion mistake. He kind of regrets that he invented it. But he invented other things as well, which lie on the basis of computer science. This thing is called a Hoare triple, named after him. So you start with a precondition, which is something, whatever, that you assume is true before your program starts. Then you have a statement that does a thing, and then afterwards there is a postcondition, and that has to be true after the statement has run. So that's pretty simple. Let's say that x equals 3. If we increment it by 1, then we know afterwards x will equal 4. QED. So that's a very simple start. So how do you apply that? There is this algorithm called linear search, maybe you know it, where you have a list of numbers or a list of things, doesn't matter really. And in this case, let's say that we are looking for the number 42. We want to know where in the list it is. So we look at the first number, it's not 42. We look at the second one, not 42, third one, and hey, now we found it. That's linear search. Pretty easy. So if you're a Java developer, you might write it down like this. Of course, in university, we used a different programming language. It's called the guarded command language, which was invented by Dijkstra. No compilers or interpreters exist for this language, except for maybe students that have cobbled something together. So we wrote it all down by hand. And we would place comments in there that indicate the preconditions of each statement and the postcondition of the next. This expression means that we assume that the thing that we are looking for actually exists in the array. And this expression means the same thing, but now also I equals 0. And then this one means that I is within the range of the array. We haven't found our thing yet, but we know that it's still there, so we need to keep looking. And after we increment I, this one basically means the same thing, but we have incremented I, so we have to update our less than and less than equals symbols a little bit. And at the end of the loop, this expression means that we found it. Of course, there's a lot more to say about this, but this is enough for now. This is what it looked like for me. This is a piece of actual homework that I had to hand in one time. And the good thing is that nowadays we don't have to do this anymore because this sucks, right? But the idea of the algorithm is important, and proving them as this way of working entails, that's really hard. Proving algorithms is really hard. So let's talk about algorithms. Another famous computer scientist is this one. Does anybody recognize the name? I guess not. Maybe if I write it down like this, or maybe if I write it down like the Romans did. That's where the word algorithm comes from. This guy basically invented that. He was a scientist in the Islamic world in the Middle Ages. He invented algebra. He helped introduce the Arabic numerals, including the number 0, which was unknown in Europe at the time. And he has a moon crater named after him as well. So, algorithm. An algorithm basically is like a cooking recipe, right? You have a number of steps, a number of instructions that you have to follow one after the other, and then you have achieved a thing. You have baked a cake, for example. And the nice thing is we don't have to prove algorithms anymore because we have libraries that we can use. And libraries can implement an algorithm for us so that we don't have to do it anymore. And it can prove that it is correct so that we don't have to do it anymore. And the library can test it for us so that we don't have to do it anymore. We only need to choose the correct one. So how do we do that? Well, the simplest thing is ask someone to do it for you. So this is Katherine Johnson. She was a person who was asked to do a lot of things in that regard. because she did manual calculations for NASA's Apollo missions. So the astronauts, they did not trust computers at the time. So if a computer calculated the trajectory of the rocket that they had to step in, they did not trust it. And they would only trust it if Katherine Johnson had manually verified this calculation. You know, that's pretty ridiculous for today's people to think that this is how things were, but they were. And in 2016, there was actually a movie about her and a few other people at NASA. So, you know, that's pretty cool. So choosing an algorithm. Linear search, if you want to search for something, is something that you could choose. You know, that as a reminder, this is what it looked like. There is another search algorithm, very well known, that's called binary search. And we've all used binary search, at least maybe the older people in this room have. If you remember telephone books, if you had to look up a number. Nowadays we just type it in our phones, but back in the day you had telephone books. A thing that still exists is the index in the back of a book. You look up the page number and then you flip through the book. You go somewhere in the middle and you think, no, that's too far. I have to go a little bit back and then a little bit forward. That's basically binary search. And what it looks like for a computer scientist is you have a list of numbers. You have to assume that they are ordered. It's a sorted list, otherwise it doesn't work. And let's say we are looking for the number 42 again. So you start in the middle and you see 58, well, that's more than 42, so I'm too far. So I go back halfway to the middle of what's on the left. And now I've overshot again, so now I go back and there I found it. So that's nice. You have to do a lot less steps. And if you're a Java programmer, this is the official implementation in the Java APIs. I simplified it a little bit to make it fit on the slide. But this is basically an implementation of that algorithm. Fun fact, this implementation has fixed a bug that has been in the implementation, the official Java implementations, for about 10 years, I think it was, before they figured out, hey, we actually have a bug in this algorithm. Which only proves again that proving algorithms is hard. Even if you trust a library to do it for you, there still may be a mistake, but at least someone else will fix it for you. And because many other people are using it, the chances of it being found are also bigger. So what's another place where you might run into binary search? That is called Git bisect. I don't know if anybody here uses Git. Who does not, right? But maybe you haven't heard of Git bisect, which is a cool feature in Git. Let's say you have a list of commits and you want to know where a certain bug was introduced. You know that the first commit is good. The bug isn't there yet. You know that now you do have the bug. So somewhere in the middle, there is a point where the bug was introduced. So what we do is we start in the middle, just like before, and we see, oh, well, here it's already bad. The bug is here. So I don't have to look at the more recent commits. I go to the left where the good ones are supposed to be. And then I look in the middle one here. I see this one doesn't contain the bug, so I don't have to go to the left anymore. And now I go to the right again. And I see, does this have the bug, yes or no? Well, in this case, it has the bug. So we know this is the commit that introduced the bug. So what does that look like in practice? Let's say that this is our list of commits. Maybe somebody can guess where the bug was introduced. Hey, you don't know. So what we do first is we check out the first commit where the project started, basically, with this hash, and you tell git bisect to start. And when you have started, you are at this commit and you can say, well, this one is good. The bug is not here yet. Then you check out your main again. You're at the most recent commit. And then you say, this one is bad. And then Git will jump to the commit more or less in the middle. And there you say, well, you can run your test script or whatever you use to check if the bug is already there or not. And let's say that this one is bad. And then it jumps to a new commit. You can try that. This one is good. Okay, so then Git knows, well, this was the commit. And that's how you can find it. And then afterward, you have to type git bisect reset, or otherwise your repository is messed up. But this is a pretty handy tool, and it uses binary search, which is better than linear search, assuming that there is some kind of order in your list of stuff. So that's cool. Let's look at some of the fundamentals below this again. Here is another scientist, not necessarily a computer scientist, but this is Hedy Lamarr. She invented the technology behind Bluetooth and Wi-Fi, which we use every day. And also she was a famous movie star playing in Oscar-winning movies. So, you know, try to do that. Okay, so fundamentals. Complexity is a very important concept. How many steps does it take to run an algorithm? So let's define something first. N is the size of our input. So in most cases, the length of our list. If you have a linear search algorithm, then you have to look at all of the elements in your list one by one. So the number of steps you take for the algorithm to complete is equal to n, basically. So that's the number of elements in the list is also the number of steps you have to take, generally. If you want to look up an element of an array and you know its position, then you only have to look up the element on that position and you're there. So that takes only one step. That's really nice. Those are the algorithms that we like the most. There are other kinds of algorithms. For example, if you want to check duplicates in your list, you have to look at the first element, then go through the list to see if there are duplicates. Then you look at the second one and you do it again, and you look at the third one, you do it again, etc. That takes generally n squared steps. You have Fibonacci, the Fibonacci sequence. If you want to calculate that one, that takes 2 to the power of n. So that's a big one. There's a cool problem in computer science that a lot of people talk about, which is called the traveling salesman problem, where you have a salesperson who wants to visit a number of towns and then go back home, and he wants to know the quickest route through all of the towns and then back home. If you want to brute force that problem, then that takes faculty of n steps, and faculty of n is a really big number. So for example, faculty of 5 is 1 times 2 times 3 times 4 times 5, and that adds up really quickly. And of course we have binary search, which we talked about just now, and that has log 2 of n steps. What the hell does that mean? Well, it doesn't really matter, just you have to know that it's way less than n. Okay, so now we know complexity. Let's abstract over that. And let me tell you about another person, Donald Knuth. He's also a famous computer scientist. Probably most famous for the fact that he writes checks to people who find bugs in his programs. So the first person to find a bug in his program will receive a check of 1 cent. The second one will receive a check of 2 cents. Then 4, then 8, then 16, it doubles. So that also adds up really quickly, but he hasn't gotten poor because of it. Because people tend to frame these checks and put them on their wall instead of actually cashing them. Because it's such an honor to receive a check from him, because finding a bug in his stuff is really hard. But yet he remains humble about it. He says, well, beware of bugs. I've only proven that this program is correct, but I haven't actually tried it. So that's one thing he's famous for. Another thing is this quote: "Premature optimization is the root of all evil." This is very famous and also taken out of context by most people who say it. The full quote is this. He says, 97% of the time optimization is premature, but in those 3% we should really take a look at it. And that is something that people who use that quote often conveniently forget about. Finally, he's famous for writing a book. I have it on my shelf, never read it, but I can say that I have it at least. And he introduces in his book something called the big O notation. And this is something that relates to the complexity of an algorithm. So the number of steps, there's a big O attached to it. So if you have one step, you have a big O of 1. If you have log n steps, then you have a big O of log n. If you have n steps, big O of n, etc. But the fun thing is that if you have 2 times n steps, the big O is still just n. And basically what we do is we pick the biggest n and then we leave out all of the rest, and that's our big O. And we do that because we don't care about the details, we just care about the big picture here. How fast does the algorithm's complexity grow if the input size grows? You can put that in a table. So big O of n is very constant. And then the bigger the big O gets, the faster the number of steps that you have to perform in your algorithm also grows. And the number in the bottom right of my table, my computer even refused to calculate it. So that's how big it is. Got an exception. If you put it in a graph, it looks like this. And we have also attached names to these big O's. So we have constant algorithms. We have logarithmic algorithms. That's a nice tongue breaker for you. Linear ones, quadratic, etc. So these are words that computer science people might sometimes use. And, now you know what I mean. But there's another way to look at these big O's, and that's this. So basically, polynomial means that the exponent in the big O, the biggest one, the biggest part of your formula, basically, the exponent of that is still a number. And once the exponent is no longer a number, then algorithms tend to explode in complexity. So why do we care about this? Well, let's talk about Alan Turing. He was somebody who cared about this because he was famous for cracking codes, which has a big complexity, of course. In the Second World War, he cracked the Enigma codes, which allowed the Allied forces to decrypt the coded messages sent by the Germans, and that helped win the war. Another thing that he's famous for, unfortunately, is that he was gay. And at the time, that was illegal in the United Kingdom. So try to imagine that. My mom is from the 1950s, and when she was born, homosexuality was illegal in the United Kingdom. And people who were found out to be gay were punished. And in the case of Alan Turing, he took it so hard that he committed suicide in the end. So he had a pretty tragic life. Then again, tragic lives lead to cool movies, I guess. So Benedict Cumberbatch starred in his, which is a good movie, but still. So disclaimer, from now on, I'm going to oversimplify things even more than I already did before. So let's talk about cracking codes. If you have a code that you're trying to crack, that's generally a difficult problem to solve, otherwise it wouldn't be a very good code, right? So the complexity of cracking a code is usually worse than polynomial, aka slow. But if you have cracked it and you want to check that you have actually done a good job, then the algorithm for doing that will often be polynomial. And this is a whole range of problems that fall into this category where solving it is very hard, but checking your answer is relatively easy. It's called non-deterministic polynomial. You can forget that word immediately. And it comes up a lot in real life as well. For example, Rubik's Cubes, Sudokus, logistics of sending packages and loading vans. Parts of Bitcoin are also NP. And of course, P, polynomial problems, have to be a different class of problems than NP problems, right? Yeah, well, actually, we don't know. This is one of the big open problems in computer science. If you manage to find a proof either way, then you can win $1 million in prize money. But of course, if you manage to prove that P does equal NP, which we don't think is the case, but we can prove. If you can prove that P does equal NP, then you can probably make a lot more money just cracking banks and stealing from them and decrypting the whole internet, basically. Because everything that we use to secure our data in the cloud, on the internet, online, depends on P being unequal to NP. So that's a piece of trivia. What does that mean in practice? So Grace Hopper was somebody very practical. You know, you have to find segues for these things when you're writing a talk. She was a rear admiral in the US Navy, but she also invented the COBOL programming language, which people may have heard of, especially if you have worked for a bank. You may have heard of that programming language. And she also invented the word bug because at the time she had a program that wasn't running correctly. So she looked at the wires in her computer because at her in that day and age, programs were written by wiring up little wires inside plugs in the computer. And she actually found a bug that was fried there and caused a short circuit. And she took the bug, put it in her notebook, and that's now on display at the Smithsonian Museum. So practically, it helps if you know the big O of the algorithms that you use. Because if you do, then you can help make sense of when you need to optimize things or not. And in order to know that, you have to know the data structures that you use in your program. So let's look at an array. This is a piece of computer memory, which contains an array, which starts somewhere in the middle of that memory. And all of these areas are not part of the array, but they exist in memory. So if you want to add something to the array, you just go to the next cell in the memory, the next spot in your memory, and just put your value there. That's nice. So that is appending something to the array, and it takes only one step because you know where the end of the array is, and you know that you can just put your value there and you're done. So append has big O of 1. Access has big O of 1 because if you know the position of something, you can just go there and find it. But searching, linear search, takes big O of n. And if you have to put something in front, it's also big O of n because you have to shift everything one position up. And then you have a free spot at the beginning and you can put your value there. A different kind of list is the linked list, which consists of cells, and each cell has two values. First, it has the actual value that it contains, and then it contains a pointer to the next cell in the memory. So this might be scattered throughout your memory instead of this nice structured thing that we saw for the array. And if you want to prepend something, it's really easy. You just create a new cell and point to the first one that you already had, and then you're done. So this has a very different profile of big O's and operations on them. If you want to access a specific element, you have to just go through the whole thing until you are at the position that you're looking for, which is basically the same as just searching for it. Prepending has order 1, appending has order n because you have to first find the end and then you can add something to it. Another data structure that we often use is the hash map. It contains a list of buckets. Every bucket has a number assigned to it. And if you want to put something into the bucket, then you calculate the hash code. You do a modulo on that hash code with the number of buckets that you have, and then you have the bucket where you should put it. So in this case, I have 10 buckets. Very easy to take the modulo. And you can see where all of the values have to end up. So if you add one, hey, now in this case, I suddenly have 2 values in the same bucket. Now I have a list of values in that bucket. So it is very important that your hash code has a very big, distribution, we call it, so that values end up in as many different buckets as possible. Otherwise, you will just end up with one bucket filled with a whole list, and your operations will be slow again. But this one has a very nice profile of big O's. Access and search, again, is basically the same. It has order n. And inserting something also has order n. You basically have to do only calculate the hash code and put it in, and you're done. Okay, so that's a lot of science. How do I do this in Java? So I have to fill in another computer scientist again. This is James Gosling. He invented Java. So that's a pretty cool achievement on its own. Without him, I guess most of us wouldn't have a job right now, or a very different job at least. So what kind of data structures do we have in Java? Well, we have lots of different types of lists, and they all have their own specific profile of big O algorithms that work on them. So we have the array list, we have the linked list. Copy on write array list is cool if you do concurrency. There's a stack, there's even a vector, and you shouldn't use that one. Just don't. There's also a whole bunch of maps that you can use. Hash map, enum map. They all have something specific that they bring to the table that can be useful in certain situations. And which one you need depends on which operations you need to be fast in your program. Then there's a whole lot of other data structures. You have a bunch of sets. You also have queues and dequeues, and everything has something unique to it that can be useful in your program. And if you want immutable variants of all of these things, then you can look at libraries like Vavor or Eclipse Collections or Guava. All of this computer science stuff also plays a role in something as trivial as variable declaration. So for example, if you want to create an array list variable, you should not do it like this. You should do it like this. So the type is a list of string and not array list of string, because if you find out later that array list was actually not the best choice, it's very easy to swap it out for something else. But if you're tied to ArrayList, of course, you can't do that anymore. And finally, something close to my heart, equality. Let's say that we have a class that models a computer scientist who has a name. And I have left out some of the boring stuff like constructor, getters, setters, whatever. And I create 2 entities, 2 instances of this. One of them is in a hash map, and the other one I have as an object, and I want to see if it is actually in my hash map or not. So how do I do that? Well, at the moment I can't, because I didn't implement equals. I cannot compare these 2. So if I do implement equals, then I can start looking in my hash map. But I still won't find it, because the hash code is incorrect. Both of these instances will have a different hash code. And that means that I will be sent to a different bucket in my hash map. So it's important to implement hash code as well, so that the hash code will always be the same if the value is the same. And now I can finally find my string or my object in the hash map. So the lesson is, if you override equals, don't forget to override hash code. So the bigger picture is, let's talk about that. I have someone that fits with that again, Margaret Hamilton. She was a person who led the team that wrote NASA Apollo's navigation software, which was a pretty big project. Actually, she is standing here on this picture next to the printed out source code of that program. And there was even an official Lego set in her honor and in the honor of some other people at NASA. So no other computer scientist has been able to say that they have been made into an official Lego figure. But more importantly, she came up with the term software engineering, the term that we still use a lot today. So software engineering, what does that mean? It's actually a bunch of disciplines stuck together. An important one, of course, is programming, but analysis, architecture, usability design, testing, those are all very important disciplines too, and they also have a role to play in software engineering. And finally, of course, computer science. And if somebody asks you a computer science question, it is important that you remember, well, here's the third thing that you can remember. The answer to a computer science question is always, it depends. So this big O notation that I've been explaining, at times it is very important, but if for your input and the thing that you have coded up, if it just runs fast enough, it doesn't matter if it is not the perfect fit for your program, because if it's fast enough, it's fast enough. No need to spend time optimizing it because it's already good enough. So if it doesn't go into the gray area, you're fine. Also, for small values, things behave very differently. So these big O's, they tend to play a lot when your input size is big. But if you have a list of only 3 elements, it doesn't really matter if you have an array list or a linked list, because your computer will be fast enough to go through the list anyway. And also, you know, picking the perfect implementation of your data structure is cool and everything, but if you have to look up what a linked hash set actually does every time you see it, maybe that costs more time than actually, you know, just using a set and being done with it. So always it depends. Okay, so let's wrap up. We're nearly at the end. One more computer scientist, better known under this name, John von Neumann. He was a prolific guy. He was a member of the Manhattan Project that invented the atomic bomb, which we all are keenly aware of these days again, unfortunately. And he was the person who came up with the word mutually assured destruction in hopes of limiting the arms race. But he also did other things. He wrote about global warming even in 1955, so, you know, pretty early. He invented merge sort, which is one of the famous sorting algorithms. But most importantly, he came up with the von Neumann computer architecture, which means that you put code and data into the same memory. And at that time, that was, you know, revolutionary. And now we think, yeah, of course we do that. I mean, why wouldn't we? Every computer does that. But he was the first to do that. So let's recap. If you only remember 3 things, the first thing should be the Morgan's law. The second one, the truth tables. The third one, it depends. Then if you want to remember more things, you can remember algorithms like, you know, linear search, what it looks like, binary search, and how it applies in Git bisect. That's something you can try out at work tomorrow if you want. Complexity and big O is something that you could remember if you ever have to choose which kind of algorithm or which kind of data structure you want to use for a thing in your program. Then this is one of the factors that you can take into account. And the data structures that belong to it, there are lots of options, as you have seen in Java. You can also remember, if you use hash-based algorithms, you should implement equals and hash code, or you will have bugs. And that's really enough, I think. So what's next? If this isn't enough for you, if you're actually more interested in this, well, keep this stuff in the back of your mind, maybe not the front of your mind, you know. Google is your friend. Know that it's out there and that you can look it up if you need it, because you won't need it every day. But if you still want to know more, there's a cool book that I can recommend. Most of the books that I read while studying computer science were pretty stuffy and boring. But this one is actually light and fun to read. I see some people making pictures, so I'll leave it up for a moment. Another thing you can do is actually experiment. So one thing I did during my studies is implement my own hash map. Because I was using a language that didn't have one and I needed one, so I implemented my own. And that was actually a fun thing to do.
What language was that?
Sorry?
What language was that?
That was Delphi. Or you can even, if you really want to dig in, you can implement your own compression algorithm. These algorithms are pretty cool and fun to dive into. And that's it. Any questions? Or did I just bombard you with too much information? Okay, I see no questions, so thank you very much.
Thanks, Jan, for this awesome talk. Well, that's the end of our meetup.